This is the story of Air France Flight 66. It was a Saturday, the 30th of September 2017, and an Air France A380 was flying from Charles De Gaulle International Airport to Los Angeles International Airport. The plane had 24 crew members and 497 passengers on board. The plane took off at 9:50 a.m. and it then climbed to 33,000 feet. Since this was quite a long flight, the plane had two first officers on board, and the second first officer decided to take the first shift. As the plane made its way across the Atlantic, the plane climbed and descended. By 11:14 a.m., the plane was at 37,000 feet. With the plane about 100 nautical miles from the coast of Greenland, the pilots got in touch with Gander Oceanic over the CPDLC, or the Controller-Pilot Data Link Communication, which is a written form of communication between the pilot and the controller. It is mostly used for clearances and things like that. The controller allowed them to climb to 38,000 feet. They were asked to report when they were at 38,000 feet. As the plane climbed to its new cruising altitude, the outer casing of the number 4 engine of Flight 66 was destroyed. The air inlet of the engine was ripped away and it fell to the ground. The plane's number 4 engine was out of operation. The wing of the plane was hit by small pieces of debris. On the flight deck, they knew that something was wrong. The plane turned 3 degrees to the right in 3 seconds, and the entire airframe started vibrating. The crew had seen similar circumstances in their simulator training, and they assumed that this was an engine surge. An engine 4 stall message came up on the ECAM display. ECAM action said the captain. He disconnected the autopilot and took control of the plane, and he pulled back power on the number 4 engine. The engine shut itself down, and the first officer pushed the engine 4 fire push button. So far, the crew had not seen what had happened to engine number 4. A member of the cabin crew entered the cockpit with a picture of engine number 4 taken by a passenger. First Officer 1 went up to the upper decks to see the damage for himself. He saw that the leading edge slats were damaged and that the flaps were vibrating a bit. The captain fell back onto his training. In this situation, Air France pilots are trained to deal with these issues using the four-deck method. Facts, options, risks and benefits, decide, execution, check. He saw that the plane's speed had fallen from 277 knots to 58 knots. He knew that they could not stay at 37,000 feet for much longer. The captain decided to bring the plane down to a more reasonable altitude step by step. They got down to 36,000 feet, then 35,000 feet, and so on till they got the plane down to 27,000 feet. ATC noticed that the plane was below its assigned altitude, and so a message came in saying, "ATC now shows you flight level 330. Is there a problem?" Air France Flight 66 declared a mayday. They were too far out for voice transmissions, and so their mayday had to be relayed by another plane. At this point, the crew needed an airport to land their plane at, and they had a few options: Goose Bay Airport in Canada and Kangerlussuaq in Greenland. They studied the approaches and the environment of the two airports. They decided that Goose Bay was the better option, even though it was further away. Flight 66 was cleared onto runway 26. As the plane was at 1,000 feet, the captain disengaged the autopilot and hand flew the airplane in. The plane landed at 3:42 p.m. They rolled down the runway, and they took longer than usual to taxi as they had to stop taxiing quite a few number of times as they had to wait while ground services picked up debris from the runway. At 4:22 p.m., the engines were shut down and their ordeal was over. They had landed the world's largest plane with one engine out, and 24 people suffered minor injuries. Once on the ground, they got to see engine number 4. The front half of the engine was all but gone. Even though engine number 4 was out, the crew made a successful, safe landing at Goose Bay. Something that really helped out the crew in this situation was the training that Air France and Airbus gave them, specifically the FCTM, or the Flight Crew Techniques Manual. The FCTM helps pilots deal with contingencies like this. The FCTM provides pilots a pathway to assimilate and act on situation when the said situation does not fall within any predefined conditions. It basically teaches pilots to think on their feet. The next question that the pilots were asked was their choice of Goose Bay as the diversion airport. At the start of the crisis, they had 3 airports that they could divert to: Kangerlussuaq, Iqaluit, and Goose Bay. They soon narrowed their options to between Kangerlussuaq and Goose Bay. Kangerlussuaq has high mountains near the airport, and the pilots were not familiar with the runway 09 approach of Kangerlussuaq, so they opted for Goose Bay. It was the safer bet, even though it was further away. After examining the engine that failed, they had deduced that the fan hub had failed. At the start of the investigation, the investigators did not have the fan hub of engine number 4. It was somewhere in the ice sheets of Greenland, so they did their best and ran simulations. The simulations they ran helped them narrow down the reasons for the disintegration of the fan hub. It also helped them model the trajectory of the ejected fan hub pieces, improving their chance of finding those pieces. 3 phases of the search were carried out. Phase 1 found bits and pieces of the fan hub and the engine cowling. Phase 2 was not successful in recovering the fan hub. By Phase 3, they had a better idea of the size of the fan hub fragments and their exit velocities. With this, they made a new ballistic model, which narrowed down the search zone. This time, they were armed with electromagnetic detection systems developed by the University of Aarhus in Denmark. It could detect the titanium fan hub below multiple feet of snow. With this new data, they went out and they did it. They found most of the fan hub, and now they could analyze the broken fan hub to see what had really torn the engine apart from the inside. Upon analysis, they found that the fan hub had cracked due to LCF cracking or low cycle fatigue inside the metal itself. But first, let's look at the material of the fan hub itself. The fan hub is made from a titanium alloy called Ti64. Titanium at the micro level has 2 phases, an alpha and a beta phase. In the alpha phase, titanium has a hexagonal structure, and in the beta phase, it has a body-centered cubic structure. As you'd expect, both phases have different physical properties. These phases occur in patches called microtexture regions, MTRs, or macro zones. In the case of the failed fan hub, the cracks started in a macro zone. The orientation of this macro zone was so that if force was applied on it in just the right way, the alloy might fail. The macro zone in question was bigger than any other macro zone that they had seen. The force applied on this macro zone was perpendicular to the macro zone. A perpendicular force like that can lead to crack formation. The parts of the engine are put under great stress, specifically cyclic stresses, and this cyclic stress can cause parts of the engine to fatigue crack at lower stress levels when compared to normal tensile stress. Exposing a part to the types of stress found in a jet engine can radically shorten its lifetime. This is known as dwell fatigue. Dwell fatigue refers to the reduction in the fatigue lifetime of a component as a result of exposing the component to a constant high mean stress during cruising, between the ramping up of the load during takeoff and the ramping down of the load on landing. And when this dwell fatigue happens at relatively cold temperatures of the engine, it is called dwell fatigue. Now, dwell fatigue is nothing new. It's been linked to failure of engines in the past, and we've known about it since the 1970s. But what really surprised everyone was that Ti64 was susceptible to cold dwell fatigue. Remember those alpha and beta phases of titanium that we talked about? Well, when there are large regions of the alpha phase titanium, it can increase the probability of cold dwell fatigue because of how the stress is applied and how the material handles stress. Cold dwell fatigue in the Ti64 alloy was very, very unusual. Other alloys of titanium are known to be susceptible to cold dwell fatigue. At the time the engine was certified, the scientific community thought that Ti64 was insensitive to the cold dwell fatigue phenomenon. They also found that depending on the magnitude of the stress that the part was under, the part's operational lifespan could be drastically shortened. So this caught the aviation and the scientific community off guard. In the case of this fan hub, the cracks started inside the fan hub, about 0.76 millimeters from the surface. Over the course of about 1600 cycles, the cracks grew, and when the cracks reached its breaking point, the fan hub shattered. The fan hub was rated for at least 15,000 cycles. As of right now, we really don't have a quick and easy way to test for these kinds of faults just yet. If the fault's there when the fan hub is manufactured, it'll stay there. After the accident, the FAA and the EASA asked airlines to inspect the fan hubs of their A380s. About 19 hubs had damage because they were struck by something, most likely due to faulty repair. After a few revisions, they started looking at fan hubs with more than 3,500 cycles on them, and one damaged fan hub was found. It was repaired. Before they found the fan hub in Greenland, they considered the idea that a faulty repair might have damaged the fan hub, causing it to fail. While doing maintenance, it was hard to remove the fan blade lock ring, and so they designed a new fan blade lock ring that was easier to remove and so would result in lesser unintentional damage to the fan hub. Right now, the EASA and the FAA are trying to bring about changes to the manufacturing process to reduce the likelihood of cold dwell fatigue. They are also batting for an inspection program to check for fatigue cracks for the parts already in service. Since this incident is pretty new, we'll have to see how they tackle this cold dwell fatigue cracking issue. Thank you for watching this episode of Mini Air Crash Investigation. A big thank you to MD Videos for letting me use his amazing footage on my videos. If you like the videos that I make, do consider liking and subscribing. It will really help the channel grow. I'll catch you guys next time. Stay safe.